Hello everyone, today we are going to talk about doing a redundancy analysis, or RDA, in R. An RDA is very similar to a principal component analysis, or PCA, except it is constrained rather than unconstrained. That distinction is a bit cryptic and confusing, so don't worry, I am going to explain it a bit better than that. A PCA generalizes information from large datasets and picks out the major trends and features of the data, so it can be used to assess sites, traits, and species behaviors. We can think of it as starting off as a multiple regression, except rather than being interested in the x and y axes, we are interested in how these different variables relate to each other. The PCA does this by characterizing where the most variation in the data occurs across all variables. So we can draw a line through the points where the most variation occurs and call this principal component 1, or PC1, which is the first axis in your PCA. We can keep doing this to explain more variation in the data, with the variation explained decreasing as the principal component axis increases. Since PCAs are trying to simplify and generalize our data, we are most often interested in PC1 and PC2, which explain the most variation in the data. In a new plot, PC1 and PC2 are our new axes, and we can generalize relationships between these variables from this. The PCA is unconstrained because it's always looking for the best variable that explains the response. An RDA builds on this, but is constrained because it's relating those responses to an explanatory variable. So let's say each of our original observations were tied to more information in a dataset, like surrounding habitat composition, for example. An RDA will use those characteristics for each observation and try to relate them to explain the relationships between response variables. This is often used to compare species relationships to environmental data. In my example today, I am using different fauna mortality data and want to compare these observations to environmental data. So my goal is to see how the mortality of different types of fauna relate to each other and how they relate to the surrounding environment. In my example, I am going to use a dataset that needs a few different transformations, so if someone following along has similar data, they know how to properly manipulate it. But don't worry, I indicate where certain steps can be skipped if you are using a simpler dataset. Let's go to R and look at this example. The libraries we need for this are vegan and ggplot2, and as always, load in your working directory. I'm going to read in my file and call it df. Remember to include header equals true if the first row of all your columns are the column names, rather than this being a matrix. I always like to NA emit the data frame as a first step, even if I don't think it has any NA values. This just helps prevent some pesky, frustrating errors in future steps. Let's quickly take a look at the data I'm working with using the head function in R, which just gives you a little sneak peek of the first few lines of the data frame. As you can see, I have site information, species abundance information, and a whole bunch of differently formatted environmental data. Some of my environmental data includes presence-absence of a ditch, road characteristics, and ratio, sum, percent, and total area of different types of natural cover. Now that we know what we are working with, let's get started. First, if you're using species abundance data like me, you are going to need to transform the data to relative abundance. If you are using presence-absence data or data that is already standardized, you can skip this step and just take a subset of the portion of your data frame that includes the species data. So for example, if my data was presence-absence, I would just be taking a subset of the columns with my species data. Now back to what my actual data is, which is abundance, I want to turn this into relative abundance so I can compare relationships between my different categories. I'm going to do this using the decostand function in my vegan package. Decostand allows you to do a bunch of different types of data transformation. In the brackets, I first need my data frame name, which is df, and the columns I want to select that includes my species abundance data in the brackets. The method of the transformation is Hellinger, which is a transformation for exactly our purpose of taking abundance data and turning it into relative abundance. And I called this transformed subset of species data spec h for species Hellinger. The decostand function is very useful to keep in mind for the future because it can easily do a bunch of different data transformations in just one line of code, including log transformations, turning data into presence-absence, and standardizations. Now that we have our species data subsetted and transformed, we want to think about the environmental data. I'm going to first show you how to do a matrix plot that shows relationships between the explanatory variables, but you do not need this step. It's not necessary for the RDA. I'm just showing you so that way you have it if you're interested in looking at the visualization. You are going to create this function that I won't get super into, but it's essentially going to look at all the data and create a series of histograms. Now to plot this, I'm going to write pairs, include the data frame in the columns, including all my environmental variables, and this panel information that is going to show all relationships and summary of histograms in a matrix. So we can see what this looks like with all our cyan histograms. Some people like this visualization to summarize what their environmental data looks like. Not actually necessary to do the RDA itself. So moving on, we want to prep that environmental data to get it ready to put into the RDA. If your environmental data is on different scales, like me, you are going to need to do a transformation. Remember, I have area and ratios and percentages and presence-absence, so my environmental predictors are really all over the place. If your environmental data is already standardized, for example, all in percentages or all in presence-absence, you can skip the transformation and just take the subset as I showed you for the species data. Now back to my data, I can do the transformation with the handy decostand function again. Now when I'm selecting my columns, I'm only selecting the environmental variable columns that are not standardized. So I have a column on ditch presence absence, and I have some columns on percentage of natural cover that I'm going to exclude from this because they are already on a standardized scale. And for the method, I want to log transform all my remaining environmental variables. I'm calling this T, E, and V for transformed environmental. Now we can't forget about those standardized variables I omitted from my decostand function. I want to add them back in now. So my complete standardized environmental data subset, E and V stand, is the combined columns, or cbind of my transform variables and the remaining variables that were already standardized. Now we are ready to do the RDA. I am going to call this spec RDA, and the function for an RDA is super easy, it's just RDA. First, I'm going to put my response variable, which is my species data, and then the explanatory, which is my environment data. This little period and then comma is just saying that I want to include all the columns in my environmental data subset for now. Let's run this and look at the summary. It looks pretty similar to the summary for a PCA. We have how our environmental variables relate to the RDA axes, and we have this info for all of our sites and for the assessed species. We are most interested in scrolling up to the top and looking at how much variation in the data the RDA axes are explaining. So RDA 1 is explaining 26.2% of variation, and RDA 2 explaining about 9.8%. Cumulative variation explained by these two axes of about 36%. We can plot this RDA using the ordplot command. I'm keeping type equal to none for now because I like adding the points and text separately so it looks a little nicer and I have a bit more control over the aesthetics. And honestly, I recommend doing the same because I don't really love how it renders automatically. I set scaling to 2 because I am interested in correlations between variables. So with this, I can look at the angles between vectors and understand the relationships. You can set scaling to 1 if you are more interested in the relationships between sites and species, which can be interpreted by the distance between these points. The rest of this stuff is just relating to label size and custom axes names. Now I can write a few more lines for all my relationships. In the background in gray, I want points that reflect my 23 sampling sites. I'm not super interested in how site relates to my explanatory or response variables, so I'm just going to let this part fade into the background a bit. I also want points for my species relationships on the RDA plot. I will make these points blue, and I want these points labeled, so I actually know which species are which, of course, and I want to make this blue as well so it matches my points. Now I want my environmental vectors and labels to be in black. Let's run all of this together and render the ordplot. From here you can see how the environmental variables correlate. If they are less than 90 degrees, they are positively related, about 90 degrees, uncorrelated, and greater than 90 degrees, negatively correlated. So forest percent is positively related to total forest, but unrelated to forest ratio and negatively related to meadow percent. You can see how these environmental vectors relate to the species by proximity. So bird mortality is correlated with wetland percent, but negatively related to meadow ratio. If you think you are done with your RDA, hold your horses for just 1 second. This is all great and went through the steps of making an RDA and creating a plot, but before finishing, there are some checks you are going to want to do to make sure you have only important variables included in your model. I'm going to go through these checks now and highly suggest you do the same before calling it a day with your RDA. First, I'm going to do a step function, which is going to create all the possible combinations of terms and select the best, most simplified model. To do this, you use the step function, input the name of your RDA, and set scope formula to the RDA name as well. And test will be perm for permutations. I'm going to call this spec RDA1 and run this. The original output of the step function is going to show some of the different model combinations and AIC scores if you're interested in how the function shows the best variables. I can look at the output summary to actually see what those variables are. As you can see, this step function reduced our environmental variables quite a bit, omitting things like ditch presence, all of our road characteristics, and some area characteristics of the natural cover variables. We aren't quite done yet. Now we want to make sure there's no collinearity between those terms that would overemphasize their importance. We can do this by assessing the variance inflation factors, or VIF, using this VIF-CCA function with the new RDA name in the brackets. The output is the inflation factor. And as a general rule of thumb, you want to omit values that are greater than 20. When we run this, we see that forest percent, meadow percent, and wetland percent are all way over 20, so these factors are inflating each other. I want to remove one of these now to hopefully bring down some of this inflation. I'm just choosing to omit meadow percent. Now I want to run a new RDA called spec RDA2 that compares the transformed species data to the environmental variables that we have left that we have deemed to be important after the step function and after we removed the variance inflation factor. Now we can run the VIF again, and you'll notice that all that inflation went down, so we are good to go. I am now going to show you how to do some significance tests in case you are doing a write-up and want to include this information. If you're interested in the R-squared, you can just write this line of code. We can also use an ANOVA to assess the significance of different things. The first ANOVA I run is of the entire model, which we can see is significant. I can run another ANOVA to see if the RDA axes are significant, which shows me that the first axis is significant. I can now run an ANOVA to see if these environmental terms are significant, and can see that meadow ratio, total wetland area, habitat area, and wetland percent are all significant. Finally, I can see if the order of these terms is significant, and can see that order does matter for meadow ratio, wetland ratio, and habitat area. Now we are finally ready to plot this new and improved RDA. I'm going to call this plot simplified model, and it is using the same code as we did before. The variation explained by my RDA axes is a little bit different, which you can see if you look at the summary of our new RDA. When I run this, I see that I lost a lot of variables compared to my original RDA, but I do know that these terms are what's important in explaining my response variable of fauna mortality. This is the plot we can use to determine correlations between environmental factors and the relationship to predicting the response variables of interest. So congratulations, you went through all the proper checks to make sure your RDA is as good as possible. If you're working on a project that you intend to submit maybe for review, these steps are extremely important. I really hope this video was helpful in understanding the process of doing an RDA in R. Check out my page if you're interested in more video tutorials in R or QGIS. If you have any other questions or suggestions, please put them in the comments. I'd be so happy to answer. I hope you enjoyed this video and found this helpful. Thank you for watching.